Consider observable O, which is n cap dot sigma. We are talking about the qubits, the sigma vector. Sigma vector is a vector of Pauli matrices, and n cap is a three-dimensional real vector such that the norm of n is 1. So it represents the direction in R3. We know that in this situation, eigenvalues of O operator are plus minus 1. And let us say O and O bar are the two orthogonal eigenvectors of O. So O acting on O will give us O, and O acting on O bar will give us minus O bar. Now, if we define the projectors or operators P plus minus, which is half identity plus minus O, then they represent projective measurements. In that case, the expectation value of operator O is the expectation value of P plus minus expectation value of P minus. But now let us define a parameter lambda, which is between 0 and 1. Then we define E plus minus as half identity plus minus lambda O. Lambda we will call the strength of the measurement. When lambda tending to 0, we have the weakest measurement. And when lambda tending to 1, we have strongest. Or projective measurement. We can see that P plus minus of projectors we defined just above are same as E plus minus when lambda equals 1. So in this case, now the expectation value of observable O is related to expectation value of E plus minus expectation value of E minus, with a slight modification that the lambda will come in the denominator. So if we have lambda very small, then we need to have much larger data, and we need to find the expectation value of E plus and minus and divide it by lambda. If lambda is very large, then it is equivalent to the projective measurements. These kind of measurements are important from the point of view of the following scenario. These kind of measurements are important in the scenarios where we want to get some information about the system, but we do not want to disturb the system too much. So in that way, if we perform measurement in E plus and E minus, then the system is deviated from the original state slightly, and that deviation is characterized by the number lambda. That's why it's called the strength of the measurement. When lambda is 0 or tending to 0, then the system is undisturbed. The state will remain undisturbed. But when lambda is 1, then the state is maximally disturbed, and it will be collapsed to one of the eigenstate of operator O. One very interesting application of these weak measurements comes in the form of reversible measurements. Let us say the observable O is nothing but sigma z. Then our E plus minus are half identity plus minus lambda sigma z. That will be half 1 plus lambda and 1 minus lambda. So these are the two effects we have which constitute the POPM. Now let us define the measurement of operators m plus minus, and they are easy to define. In this case, we just say square root of these, that is plus minus minus plus and plus minus and minus plus. So our m plus measurement operator is 1 plus lambda over 2, 1 minus lambda over 2, and m minus is square root of 1 minus lambda over 2 and 1 plus lambda over 2, and rest is 0. Let us recall that E plus minus is m plus minus dagger m plus minus. Since m plus minus are the Hermitian operators, so m dagger is same as m, so it's same as m plus minus square. So e plus minus are m plus minus square. Another interesting thing here is m plus and m minus both being the diagonal matrices, they commute. So it does not matter whether we have m plus m minus or m minus m plus, they will give us the same result. Now let us consider the measurement setup. We have a measurement setup box. The input state comes here, psi. Output goes here. This is plus and this is minus. The output state here is m plus psi, proportional to m plus psi, and here it is m minus psi. The probability of this p plus is the expectation value of m plus dagger m plus psi, and similarly p minus is psi m minus dagger m minus psi. We can see another interesting thing we can see is m plus m minus is 1 minus lambda square over 2 times identity, and that is same as m minus m plus. So what does it mean? That if we have a system going in the experimental setup and the system comes out after giving the click, and then we perform the same measurement setup, this was the measurement setup m, let us call it m, the same measurement setup, we pass it through again, then again it will have plus minus plus minus. The state here was m plus psi, a normalized state, and here it was m minus psi. State here is m plus square psi, m minus m plus psi, m plus m minus psi, and m minus squares. But just now we saw that m plus m minus and m minus m plus, they are proportional to identity. So this acting on psi will give us the state psi back. So these are the state psis. This will happen with the probability 1 minus lambda square over 2, and here it will happen with 1 minus lambda square over 2. So total probability of getting the state back psi is 1 minus lambda square. The probability of retrieval is 1 minus lambda square. So we start with the state psi, doesn't matter what state it is, as long as it is a qubit state. We perform a measurement in the chosen measurement basis, measurement operators, then we get either plus click or minus click. We expose the system again to the same measurement, and then we get m plus square, m plus m minus m plus, and m minus square operators acting on the initial state. Two of them will give us the state back, the original state psi back, and the probability of this happening is 1 minus lambda square. So in that way we can reverse the measurement and we can retrieve the system back. Now can we use it in some way? Now first of all, let us say that if we simplify it, we have a state going in, we have measurement setup, we get in the same arm we get either plus or minus outcome. We send another measurement setup and another measurement setup, and let us say we do it few number of times. Then the output state is proportional to product over I m I from 1 to q acting on psi. That will be the output state, and then I MIS, let us say, where or SI, where SI is from the set plus or minus. So ith measurement outcome is either plus or minus. And the probability of retrieving the state in this case, because all the m plus and m minus commute, so it's just a matter of being the number of m plus equal to m minus, number of m plus equals number of m minus in this set will imply that we have retrieved the state psi back. And probability of that happening is the number of times this thing can happen, that is the q choose q over 2 times the probability of this thing happening, which is 1 minus lambda square to the power q over 2. So total will be q factorial over q over 2 factorial square times 1 minus lambda square to the power q over 2. So with this probability, if we repeat the experiment q number of times, then this is the probability that we will retrieve our original state back. Now, how can we use it in any useful way? Let us say we have the measurement setup, and we say it goes up for plus measurement, it goes down for minus measurement, down, up. We discard this, we go down, we go up, we discard the down one, and this one is the state psi back. Now we can send this in the loop. So we had psi here, we perform measurement m, we perform the same measurement again, and with certain probability, that is 1 minus lambda square, we get the state psi back, and we can put it in the loop again. If we can manage to do for some lucky particles this whole measurement n times with the same particle, then this must be equal to having one particle going in the measurement setup, getting us two outcomes, and another particle going in, getting the two outcomes, another particle going in, getting the two outcomes, and with n particle we repeat this measurement. So one particle going through this setup should be equivalent to n particle going through the measurement setup. Of course, we can only consider the result at these points. So we calculate the number of clicks in the m plus and number of clicks in the n minus at this point, and then the second phase of this measurement is to retrieve the state again. So the probability of getting plus should be n plus over n, and probability of getting minus should be n minus over n, and these are the expectation value of E plus and E minus. And from here we can calculate all the expectation values and stuff like that of the operators. We can estimate the state. Whatever we want to do, we need the expectation value of the POVM elements, the effects. And these clicks n plus and n minus will give us that expectation value. If we are given, let us say, an ensemble of quantum system and they are in the state identity over 2. Okay, and we have been given additional information that either they are prepared in 0-1 basis or in plus minus basis. Yeah, that is either in the eigenbasis of sigma z or in the eigenbasis of sigma x. So either the state identity over 2 is 0-0 plus 1-1 over 2, or it is plus plus minus minus over 2. Now, can we figure out whether the preparation basis was 0-1 or plus minus? What we need to do is we take particles from this ensemble and send through this setup. We send one particle, we see n plus clicks and minus clicks, we retrieve the state, we again do it. So some particle will just go through this setup once and they will come out by getting in these two arms. Some particle will go in the second round, some particle will go in third round, and with probability given by the number we calculated earlier, we will get some particle going through this circle n number of times. And when the n is large enough, then we calculate n plus and n minus probabilities numbers, and from there the p plus and p minus probabilities, and from there we can calculate the expectation value of E plus and E minus. Now, expectation value of E plus minus in the state 0, that is 0 E plus minus 0 will come out to be 1 plus minus lambda over 2. So either this, so for E plus, the expectation value of E plus in the 0 state is 1 plus lambda over 2, and expectation value of E minus is 1 minus lambda over 2. E plus minus in state 1 is also the same, just with the different signs. But E plus minus for the state plus minus is actually half. So the expectation value doesn't matter whether we are in the states plus or minus, the expectation value is always half. So these are the expectation value, these are the probabilities of plus minus in the state 0, probability of plus minus for the state 1, and probability of plus minus for the state plus minus. But we are doing a stochastic process here. We have n number of events happening, and we get n plus and n minus clicks. So when n is very, very large, then n plus minus over n will tend to p plus minus. But for small n, it will not be exactly equal to p plus minus, but it will be a Gaussian distribution around this mean value of p plus minus. It means for 0 and 1 state, the probability distribution or this expectation values will look like this. For this is half, this is half plus lambda, and this is half minus lambda over 2. So now if we had very, very large n, then we will get exactly here the expectation values. But if we have small n, then it will fall on this curve. For 0 and 1. We don't care whether it was for 0 or 1, but this one will be for 0 and this one will be for 1 when we are doing E plus, and the other way when it is E minus. So that is fine. For plus minus state, this graph looks entirely different. It will be centered around half. So this striking difference between the probability distribution of 0, 1 and plus minus can be used to estimate the preparation basis of the input state, which was I by 2. So what we have to do is we send it through, send the particle from the ensemble one by one through the experimental setup, and then we wait for some particles to go through the loop n number of times where n is large enough. We take the probabilities or n plus minus from there and we divide them with n, and we repeat this experiment many, many times. We'll get a set of n plus, we'll get a set of n minus, and then we plot the frequency of those n plus and n minus divided by n, normalized with n, on a graph. If the graph looks like this bimodal distribution, then we know the preparation basis was 0, 1. When it is a unimodal distribution, then it was plus minus state. In that way, it seems like we can distinguish the preparation basis. But quantum mechanics says that once we prepare a quantum system, we cannot distinguish the preparation basis. Density matrix is all the information we have. We cannot have the information about the preparation basis. We discussed this point when we were discussing about the preparation basis and decomposition of a mixed state into a mixture of pure states. Once the density matrix is constructed, there is no way to retrieve the information about the quantum system. But here it seems like we have a method to retrieve the information. So let us see if it holds. Let us consider another scenario. We have two qubits. They are far apart and they are in entangled state. The one qubit is in Alice's lab and other qubit is in Bob's lab. Let us say the state of these two qubits is 0, 0 plus 1, 1 over root 2. Interesting thing is, if Alice performs measurement in 0, 1 basis in her lab on this on her qubit, and she gets 0 state, 0 outcome, Bob will also get 0 outcome. if he perform measurement in sigma in 0, 1 basis. If Alice get 1, Bob will also get 1. If Alice perform measurement in plus minus basis and she gets plus, if Bob also perform in plus minus basis and Bob gets, then Bob will also get plus. If Alice gets minus, Bob will also get minus. This is the property of this entangled state. That if you are performing measurement in plus minus 0, 1 basis in both the labs, then the results will be identical. If you perform measurement in plus minus basis, then also results will be identical. So this is the eigenbasis of sigma z. This is the eigenbasis of sigma x. If both perform measurement in sigma z, the results are identical. If both perform measurement in sigma x, results are identical. Okay. Now they are far apart. They can be as far apart as possible. Entanglement will survive if there is a way to distribute entanglement between these two parties. So if let us say Alice wants to send some information to Bob without communicating over the classical network, then what they can do is, let us see if she can send 1 bit of information. Then that 1 bit can be logical bit 0 or logical bit 1. It can be outcome of a match, cricket match, or it can be an outcome of results of a voting of some type. So the protocol they can follow, which is pre-decided, that if the measurement is done in sigma z, then it would mean that the logical bit Alice is trying to transmit to Bob is 0. If the measurement is done in sigma x, then the logical bit Alice is trying to transmit to Bob is 1. The measurement in sigma z implies 0, measurement in sigma x implies 1. When the measurement is performed in sigma z, Alice will get answer randomly, the outcomes will be randomly zeros and ones. So her average state on Alice side will be identity over 2. This is in the Alice lab. And Bob's lab also, it will be identity over 2. But this identity will be 0 out of product 0 plus 1 out of product 1 over 2. So is in the case of Alice lab, Bob's lab. If the measurement is performed in sigma x basis, then the identity will be plus minus over 2, and Bob will also have the same state without even Bob knowing. Just because Alice performed measurement in sigma x, Bob's state will be a mixture of plus and minus. If the Alice perform measurement in sigma z, then the Bob's state will be a mixture of 0 and 1. So now, after Alice has performed measurement, Bob has an ensemble of particles, quantum systems, where the average state is identity over 2, but it can be either a mixture of 0 and 1 or a mixture of plus and minus. This is exactly the scenario we discussed just now in the previous section, where the Bob's task is to find whether the preparation basis was 0, 1 or plus minus. And Bob can perform this whole algorithm, whole protocol, and see whether the distribution he gets is the bimodal or unimodal. And accordingly, he can infer whether the measurement was performed in sigma z or sigma x. Hence, the bit was transmitted was 0 or 1, the value of the bit. In that way, Alice can instantaneously transmit 1 bit of information to Bob over arbitrary distances. This is in conflict with one very fundamental principle, and that is the superluminal communication. Nothing can travel, no message can travel faster than the speed of light. But it seems like from this protocol, that is violated. There are certain things which we cannot violate, and superluminal communication or causality is one such thing. So there must be something wrong with this protocol. The reason for this scheme to show this kind of contradicting, this kind of worrisome results can be explained as follows. Let us consider the experimental setup again. We have the box which with the measurement operators m, plus minus, this is plus and minus, and we send the state psi in. and the output is m plus psi and m minus psi. So let us recall that our effects E plus minus 1 over 2 identity plus minus lambda sigma z. Our aim in this experimental setup is to get the information of 0 state and 1 state which correspond to lambda tending to 1. So when lambda tends to 1, when lambda is equal to 1, then E plus minus are 0 0 and 1 1 projectors. So in that case, we get this is the strongest measurement. This is the most perfect measurement we can have. And when we don't have such strong lambdas, when we don't want to have very large lambda, that is lambda tending to 1, in that case, we still want some information about the 0 and 1, but not exactly, but some approximate information. What I mean by information is the probability of 0 and probability of 1, or probability of something close to 0 and something close to 1, which is possible when lambda is 1. But when lambda is not 0, then we don't get 0 and 1, we get 0 tilde state and 1 tilde state, where 0 tilde is defined as m plus acting on psi, or let me say proportionally because it's not normalized, and 1 tilde state is defined as m minus. Since lambda is not, if lambda is less than 1, so it's not equal to 1, then most likely 0 and 1 in a product is not 0. So they are not orthogonal. Unlike in the earlier case where 0 and 1 were orthogonal. So we can write 0 tilde as some coefficient a times 0 plus some coefficient b times 1. Similarly, we can write 1 tilde as they are not normalized, so a and b did not add up to 1. C tilde times 0 plus d times 1. Since they are not orthogonal and they are two-dimensional states, so we can decompose them in, we can expand them in 0 and 1 basis, and A, B, C, and D are some coefficient yet to be determined. We want information about 0 from 0 tilde state, but 0 contains 1 state also. So this is what will give us false positive. So sometimes we get a click in 0, but there was no 0. There was 1 actually. And similarly, this term here will give us the false positive. And these are the terms which make possible that when we for the first measurement we have tilde, and the second measurement we have 0 tilde and we have 1 tilde. So these are the states which gives us false positive to start with, and these are the states which makes the reversal of the measurement possible. So these are the terms like the 1 in 0 and 0 in 1 tilde. These are the terms which are making the reversal of the measurement possible, so that we can use the same system again because we are getting the state psi back. But these are also the terms which dilutes our measurement outcome. Why do we need large number of measurements to get the same amount of information as with weak measurement as we need for stronger measurements? Because these kind of false positive dilutes our result. Hence, these scenarios where the measurement reversal happened contains no information about the system at all. But let me repeat it again. Since our measurement is weak, the outcome we have 0 tilde and 1 tilde, they are not orthogonal. They should be orthogonal, and they will be orthogonal when lambda tends to 1. Then 0 tilde will converge to 0 and 1 tilde will converge to 1. But when it is weak, then 0 tilde has 0 and 1, and 1 tilde has 0 and 1. So the presence of state 1 in 0 tilde is what is making the measurement reversal possible. Similarly, presence of 0 in 1 tilde is making the measurement reversal possible. But also 0 in 1 and 1 in 0 tilde is what is causing the false positive, is causing a click when there should not be any click. Hence, we can claim that the scenarios in which the measurement reversal happened contains no information about the system or the state of the system side. So those cases cannot be used to infer any information about the system.